So last time, I think Maya got everyone pretty far. I mean, you were simulating these concentration profiles throughout throughout your battery. And suppress some of these outputs. So I just grabbed this from her. So this all looks pretty good. I'm making sure that this H2 is spread out over the entire. It's spread out over. Yeah, the whole area, the whole length. Yes, she got you in a good spot. So, I mean, the next step really is, so you're basically just calculating the equilibrium potential at this point. And so what we want to do now is we want to start taking into account the different over potentials. So the first thing I want to do is I want to show you kind of a cool thing that MATLAB is kind of, it's a relatively new thing in MATLAB, not crazy new. If you take this code and hit copy and you go to home, they have these new scripts called live scripts. Maybe some of the people in 3800 have seen these. If you paste your code in here, you'll see you'll have two windows. It's basically the same. You can also add in, it usually looks a little bit nicer, but the kind of the cool part about it when you go to run, I don't know if it's always slower. That might be a downside if the code is always runs like this slow. But it's kind of neat. You can kind of see it go through your code. And the nice part is it plots all of the windows on the right over here. So you don't have all these stacks of windows coming up all the time, which is kind of cool. And so you can kind of see both things that you're doing. So I might suggest first you can start to do things in this way. The next couple of things are maybe just to clean up the code a little bit. So what you'll see is that a lot of these have the same inputs in them, right? So if you want to change something like the time, you'd have to go in and change it 5 times. So what I would typically do is let's start to put some of these inputs into kind of some inputs that we can put in up here, so we don't have to put them in multiple times. So let's put in our initial concentration for the kind of the high side. So those are the ones that'll start high, like the 1500s, right? And let's start these at 1250. So this is moles per meter cubed on the for the kind of so this would be both for VO2 and V2. So those are kind of like your reactants, right? So and then we'll change in here. This will be CI high. And the nice part too, you also see it does a better, these live editors does a better job of recognizing. Like if you start to type something, it'll kind of find it for you. I think the other one has shortcuts like that too, of course. That's supposed to be 1250. And we'll do one for low. So because we're going to start to try different things today. CI low, and this is for VO and V3. And we'll start maybe this one at 250. So this will be CI low. This one will be CI low. And then we should also put in, maybe the different sections will have different lengths, but we should probably discretize them for the most part. So we'll have time, so that'll equal 60. This is the total simulation time in seconds. And then we'll have dt, which will be 10 milliseconds, or 100th of a second. So this is your time step. And then we'll do dx. And that's going to be this 1e to the negative 5. So this is your distance step in meters, and this is in seconds. So I think this is 5. 1, 2, 3, 4, 5. Yeah. So then I'm just going to start going through and replacing these. So this will be dt, 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 right? Down here, dt. And then I might, for time, since I don't want to type time all the way out, I'm just going to copy it. I'm going to come in here. I'm going to switch this to time, 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 time. And then this one will be dx, 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 and then so I'll probably do the same thing for, because I even might want to, the other thing is I might want to use those variables later, right? So it's just useful to have them. So I should also have an area. So this is going to be equal to this value. This is your area. This is active area in meters squared. And then we also probably want to have a current, right? And that's going to be equal to this value, 1 e to the negative 1, it looks like. 1 e to the negative 1. So this is in amps. So that'll be, but you make sure you keep the signs, right? Because the signs are important on this, right? Current, and then copy, paste. We're going to clean this up a little bit. Paste. Paste. This is current. Here, one sec. So at this point, and so this, and also too, what I would probably like to do is I would take this portion of this code, because one thing I always have trouble with is like figuring out, wait, which one of these corresponds to what, right? So if you come in here and you put above it, and you know, okay, these are the inputs. So you have your initial concentration, your diffusion coefficient, your current, your area, your length, your space, your step in space, your step in time, and then your time step. So hopefully you're getting that. Okay, so there's one other thing that I need to do. Okay, so the other thing I should point out, so for the Nernst equation, right? So let's write our so we had our full reaction here, right? So we have just give me one sec. So we have on our positive side, right, we have this VO2 plus water going to VO2 plus 2H positive plus an electron. On our negative side, we have V3 plus an electron going to V2. So these are your two equations, right? Your whole cell equation is going to cancel here, and you're going to have your VO2 plus V3 plus water is going to go into VO2 plus V2 plus 2H plus, right? I mean, so you could arguably track the concentration of water at the reaction site too. But since it's mostly water, I think it's a safe assumption that you don't need to, it won't be changing all that much, right? All these things are just dissolved in a ton of water. So, but if you wrote the Nernst equation, right, you'd say, okay, the equilibrium potential is going to be equal to your equilibrium potential at standard conditions plus RT over NF, and you'd have natural log, and you'd have of all of your reactants, so you'd have concentration of VO2 plus over the concentration, some standard concentration, plus the concentration of 3 plus over some standard concentration, or times that, and times the concentration of water over some standard concentration of water, C naught, and then right, you divide this by all of your products, so you'd have B. Hopefully, did I write these equations right? I think I wrote them. Right. So you'd have VO2, concentration of VO2 plus over concentration naught times the concentration of V2 plus over the standard concentration over the concentration of protons squared over the standard concentration squared. So what you'll see is normally, sometimes I'll write this and I'll just drop the standard concentrations. And the reason that works is usually because you have the same number of species on the left and the right. The reason that doesn't work in this case is because if we ignore water, we have 1, 2 species on the left and 1, 2, 3, 4 species on the right. And so you'll see like, and so if we just assume this term is 1, right? That term's 1, so this term kind of goes away. This C naught cancels with this C naught, this cancels with this C naught, and this cancels with this C naught, but you're left with a C naught squared that you need, right? So because you need this to be unitless, and so the only way this will all be unitless is if you leave this one in there. So let's go back and look at our code. So you have VO2. Yeah. This is interesting. So oh, okay, this is good. I noticed what I did wrong now. So the way these equations are written, right? This is the charging reaction here to here. So in terms of the in terms of the voltages, this is actually the reactant. So we have to flip this, sorry. So this should be flipped. Because Maya, you guys did that, right? So that's flipped. Because these are for during discharge, these are actually products, and these are the reactants. Okay, so you flip those, so 1 over. So that looks, so everything should look right in your code. So you have log VO2, and you have this concentration of protons, right, squared. But what you should have is you should divide in your division down here. You should have times 1,000 squared, because 1,000 is the standard concentration, is that C naught. So that'll correct the units in this. So that should look good. So let's run our script, and let's make sure everything's still running okay. Could also comment out this. So. All right, so that looks good. So it still looks good. So these start at 250 and go up, and 1250 and go down. This seems like it brings the voltage down closer to the equilibrium potential, which is like around 1.26, which is good. The reason it's a little bit high is because in general your concentrations are above the standard concentrations, so it makes sense it's a little bit high. And this looks good. All right, we can let's clean some other things up. We'll let's put some we'll put some labels on these just for now. So this is time in seconds. This is going to be concentration in moles per meter cubed, right? And then you'll need a legend. So legend. What was the call out here? It's just you put them in a row like this. Do you remember, Jose? Is it just like VO2, comma?
Yeah, comma, yeah.
Yeah.
Yeah, but in quotes.
So let's track. So, and then this will be our figure 2. We're gonna change. Let's change our figure 1. Will be the actual voltage. We have figure 1, figure 2. We'll make a figure 3. A figure 3. We should also track the other species that we care about. So make this one for V2 and V3. Sorry, I'm gonna take this real quick. I'm supposed to get some injection in my back later this week, and I need to cancel it. All right, so I think, so and I changed this to match this. So I think we're looking like we're in business at this point. Let's try running it. That way you can track the concentration of everything. Let's check out our code now. This looks good. So we can see kind of our initial VO2 goes down, our VO is going to go up. That's to be expected. Our V2 is going to go down, our V3 is going to go up. That looks good. You can see that our battery should die. Now we can see what's causing our battery to die. This V2 concentration, right? This thing is running out after about and so keep in mind, this is at the surface, right? This is concentration. Just keep in mind, this is not like the overall, this is concentration, at surface. What's going on with my dog? You can probably hear him barking in the background. Right, and so you should expect your cell to die here at about 32 seconds or something, which corresponds to this graph now, right? So that's kind of cool. You basically figured out, well, how do you make your cell perform better? Well, you need to find a way to get V2 to the surface at a faster rate, right? Let's also plot the protons. That'll be interesting. So we just need, this will be figure 4 actually. Actually, in live scripts, you actually don't need to call the figure label. If you want it to plot on the same one, you have to say hold on, and then afterwards you'll say hold off. Well, let me confirm that actually. It'll be interesting to see if you even need the hold on command. So you can tell it always takes time to run through this part of the code. Yeah, so after the hold on, it does everything, right? So you have to give it a hold off. So that just basically means hold on basically means still use that current figure, and then so you do hold on, and then so this would be concentrations of H. I think that would be called the concentrations of H at the surface, and this doesn't need 2 legends, it just needs 1. This is probably a little bit high. I think the initial concentration is about 3 molar. So to convert this to molar, it should be in thousands. So try running that. I'm gonna make sure my dog's not like stuck in the fence or something.
Yeah, I hear you. What's up? Come here, come say hi. Come here, come say hi. Buddy, he's the one barking in the background.
He got stuck behind the air conditioner. He didn't know how to get out. Oh, but she's stuck. He was kind of scared because there's like tubes on one side and wood on the other. All right, so let's run this one. So let's see here. So we got those two, those look right. This is still dying at about 32 seconds. We see slowly we're consuming our protons and producing water. That looks good. All right, this all looks good. Okay, so what we want now back. What is this? We can also add. We're going to be adding to this plot a lot, so let's add some labels to it. This is time, and this is cell voltage. Okay, so the first thing we'll want to do. The first thing we'll want to do is to find the kinetic overpotentials, right? So the way we're going to do that is we know that the current that flows kinetically. And so this is just going to be the Butler-Volmer equation, which you've already seen, but super fundamental to electrochemistry, and then reduced down to the Tafel equation. But so you have some exchange current density. So this is the rate at which it goes forward and back, right? And keep on remembering, this is like you have the energy of your products, right? And then you have the energy of your reactants. And at equilibrium, they'll just go back and forth at the same rate, right? But if you lower down the energy of your reactants, right, the barrier to go this way is much higher. So this is high barrier, right? You have to go from here to here. That's a very high barrier, right? To go forward, right, it only goes here to here, right? And so that causes a forward reaction, and you do this with voltage, right? So that you take the system out of equilibrium, and you favor one direction, right? So and this rate at which this just hops back and forth is the exchange. It's called the exchange current density, and the total current is related to this by so formally it's the concentration of the, let's say, of like the reactant at the surface over concentration of the reactant in the bulk. So surface, right? Times the exponent of alpha NF over RT times the over potential. So this distance right here is the over potential. So that's how much you change that voltage. And that's going to be minus the concentration of your product on the surface over the concentration of your product in bulk times your exponent of 1 minus alpha NF over RT times this is still an exponent, times eta. All right, so this is your forward reaction. So this is forward. This is your reverse reaction. And your I naught is usually expressed as there's a fundamental constant that kind of needs to be measured, or some advanced simulation needs to be done. So this is your like your kind of rate constant, reaction rate constant. And so this is going to be K naught times Faraday's constant times the concentration of your reactant in bulk to the power of alpha times the concentration of your product in bulk times the power of 1 minus alpha. Typically, to start, alphas are around 0.5. So typically, we'll just say 1 minus alpha and alpha are 0.5. So you've probably seen this kind of Butler-Volmer equation before. Typically, actually, there's a, yeah, I mean, this could be on a per area basis right now. So this is current per area. But you could just multiply it by the area, right, to get the total current. So, you know, I is equal to I times A. So, but let's assume, but you can immediately see why this is hard to solve for, right? And the way we've set up our code, or most codes, because we prescribe I, and we want to find this eta, this overpotential, this change in voltage, basically. And the issue here is we can't solve for eta explicitly as a function of I. So you'd have to do some kind of implicit kind of iterative solver in order to find what eta in both of this would satisfy I. So maybe in a future one, we'll have just a little thing about how do you write implicit solvers in MATLAB. But I'm sure if you look that up, you could find some good examples of doing that. But what we can assume is the reverse is negligible. So we always say, okay, well, we're going, you know, I'm going to go at high enough currents where the reverse is negligible. A good discussion would be like how can you know whether that's negligible? Like what has to be the size of the overpotentials, right? And so you'd have to compare this term to see basically. And this would be like, I would say if this term is, you know, 10 times bigger than this term or more, you could probably start to ignore this term. But so we ignore that term. And then we basically have I equals I naught. You have this concentration of the reactant at the surface over concentration of the reactant in the bulk times the exponent of alpha NF over RT times your overpotential, which is what we want. This is what we want. This is what we're trying to find. We want to know what is the overpotential associated with the kinetics. But now we can solve this equation. So that's the good part. So we divide this over, right? So at this point, and then we take the natural log of both sides. So we'll have I over I naught. We have concentration of the reactant in the bulk on top now, and concentration of the reactant on the surface here, right? And then what we're gonna have is equal to exponent alpha NF for RT times the overpotential. So now we just need to take natural log of both sides. That'll cancel that, natural log of this. And then we divide this over. So we'll see this eta, this overpotential, which we want, is going to be RT over alpha NF times the natural log of I over I naught times concentration of the reactant in bulk over concentration of the reactant at the surface. Sometimes this term is often ignored. Probably not intelligently so, though. I mean, a lot of people will fit this data. Like they'll put in a fudge. You could put a fudge factor in here, right? This K naught right here, right? You measure and fit this. So this is kind of a fit factor, right? So if if you make a mistake by ignoring a term, typically the way they make it so it's reasonable is they have some kind of, they've modified their fit or their fudge factor. So you got to be careful sometimes. But let's do this, right? And so let's go into our code. And and this happens on both the positive and negative side, right? So we're gonna have to do, so I naught on the positive side is going to be equal to, so we're gonna have, so we're gonna have n, which is, well, n is 1, so we just have f times k naught positive times concentration initial on the high side to the half power, so that's alpha to the power of alpha times concentration initial low to the 0.5. Right, and so this is gonna give us an answer in, this will actually be in, so this is per meter cubed. Let's put in the k naught first. K naught. I found some k naughts. K positive. So we'll call this k naught positive, and this is going to be in meters per second. So this is going to be coulombs, and we're going to end up with per mole. So I cancel. So the concentrations are going to give us a meter cubed on bottom. So we're going to have a per. We'll have a per. We should have a per meter squared. So this should be a. Units of this will be in amps per meter squared. And then we can solve for the overpotential, right? So we'll say eta, so that's like the symbol, eta kinetics on the positive side, right? And that's going to be equal to, we had RT divided by our alpha, which we assume is 0.5, although we could probably get better data, times n times f. So we have that. Let's check my notes here real quick. Okay, so this all looks good. And it's going to be times log. So log is natural log, and we're going to have our current that we pick divided by area. So that's our current. That's our current density. And this term is going to be divided by our I naught positive. And this is going to be times. So the hard part here is this thing's going to be a function of time. So we need to come and get the concentration of the reactant. So on the positive side, our reactant during discharging is going to be our VO2 plus. Our VO2 plus concentration. And we'll see if this will able to handle this vector notation. And this is going to be divided by CI high, the initial high concentration. if you want to clean up just the way it looks for you, you could say this is like, so this is the current density, current divided by area, divided by I naught, that whole thing times the concentration at the surface. But I think that should be reversed, right? That's what our derivation showed. Yeah, so it should be actually the opposite. It should be the bulk concentration, which is what we start with, divided by this concentration is VO2. Right, and then we can run a similar thing. So this is kinetic over potential positive electrode. So we could run the same thing for the negative electrode. This is the number I had for on the I found on the negative side. So this will just be negative. I'll switch that out. 2.21. Here's 7. This one is still right. The I naught is still right. So for this should be K negative. Eta kin, and we need to do the negative. This is all right. This is all right. We need I naught negative. Change this. This should be all negative. And then in this case, we need on the negative side, our reactant is the V2 plus. So the concentration of V2. So let's see if we get any bugs. If they don't like the fact that we might need a dot here. Because you're multiplying, you want to do it like piece by piece. You need the period. Oh, I don't think I finished this. Oh, whoops. Okay, so a couple things we need times RT. And this period should not be here. It should be before the concentrations term. Okay, so it looked like it ran, right? No error messages. This all looks good. So we want to let's check our eta. Let's check our cool. So they look reasonable, right? They're not like 10 volts, you know, they're a fraction of a volt. So our total eta from kinetics is going to be our eta kin negative plus our eta kin positive. Right? And so we'll call this E diffusion. So this, because this has the terms that account for losses in diffusion. What else do we? So then we could do a couple, right? So we could do, so we'll do plot E diffusion. We'll do hold on, and let's do another one where we do the voltage just from kinetics and diffusion. So E kinetics will be equal to E diffusion minus eta kinetics. And so we'll also plot that. This will be kinetics. And we'll add a legend. And so we have diffusion. We're gonna have kinetics. Here, just one sec. Someone's outside my house.
Hey, Dr. Bachman, you're still muted.
Okay, let's run it. Let's see what mistakes we found. Um, continue. Oh, I think I accidentally added like a stop here or something. Clear breakpoint. Try running one more time. I'm not super familiar with these live scripts. I'm kind of just starting to learn them too as I go, but I kind of like them. I think they're kind of cool that you don't have all these windows popping up, but obviously it's giving me some like error message here. So it has imaginary parts of complex X or Y arguments are ignored. Okay, you're ignoring them, but you're also not plotting. You're not giving me the plot I want. I don't like that it's not telling me exactly what the error is, but I guess we'll have to do a little more debugging. The E diffusion shouldn't have too much. That one's, so it starts to get a little wonky after, once the battery dies, you'll see it starts to have these imaginary components. So see this I, so that means it's going a little crazy, but that's to be expected when you have negative concentrations in these log equations. So let's see our Ekin. It's about roughly the same time, if not a little bit later. Starting to go a little wonky. Yeah, 3457, I think that's the same number. All right, so why are you not liking to plot this then? So ediff, ekin. Oh, it's because I didn't do hold off. Huh, that's interesting. Let's try running it again. So this is the plot. It just has It just has everything built into one. So these little things must say warning imaginary. All right. So here's the losses. Here's the losses associated with the kinetics, right? So here's kind of the voltage with diffusion, but if we add the kinetic terms on, this is what we're going to get for our battery performance. So so the next thing we want to do is the other losses, right, are the IR losses, right? So do eta, well, we should say R is like 0.6, let's say. So this is in this is ohms centimeters squared. So this is area specific resistance. And then so your eta IR is going to be equal to your current divided by the area of the cell times this R value. This is, we can just say it's 1. Let's put a little bit on the high side. It's that order of magnitude. Now this depends a lot on your cell geometry, so it's not as like fundamental of a parameter as this. This depends a lot on your cells, what your cell's actually made of. So you have and so we're gonna have to make one more. So we'll say E IR is going to be equal to E diffusion minus eta IR. And if we wanted to, instead of doing the whole diffusion, we could always start off with just the very first value of the diffusion, like E, like the initial. So we could say this is this might be more insightful. E diffusion of 1. And this might be E diffusion of 1. And then you can really see just what is the contribution of each term. Oh, this is not what I wanted to do. This is E negative. So so the kinetic voltage, we'll just say it's, we're not going to include these other diffusion losses. We're just going to say what would be the losses from this initial voltage, basically. The same thing here. We'll say what are the losses from the very first one, and then we'll put them all together, and then we'll have an E total. And that's just going to be E diffusion minus eta from the kinetics minus eta from the IR. So we'll just have to add these other two. No, we don't need more hold-ons. So we have eta E diffusion, we have kinetics, we have EIR, and then we're going to do the total voltage. E total. So let's run this. This should be eta, not E, eta kin. Eta IR, so we need an underscore. That's kind of cool. It's like auto recognizes what you would think you would want. funny. The computer. Probably be a good time to save something like this. Yeah, you don't want spaces in these. All right, so now you obviously see something's wrong, right? So this is per centimeter squared, so we need to convert it to meters squared. So I knew the centimeter squared number kind of off the top of my head, but I need to convert it. So it should be e to the negative 4, because everything else here is in meters. Let's try to run that again. The annoying part is like it has to run through this whole solver every time, but I don't know why it takes so long to go through this plotting portion of it. So maybe that's the downside with the live scripts. It looks like the code just runs slow. Like really, why did it take you that long to plot this? So we should have diffusion, kinetics, IR, and total. So you see the IR won't really change any. So let's see what EIR is, basically this constant value. Oh, so so you see it's, the issue is, so EIR, we have to make it from, so from 1 to maybe like length of E diffusion. So EIR is not that long, so that's one of the reasons why it's having trouble. That's why I didn't plot that one, but plotted the others. So I didn't run this in the background. So, okay, so the other thing, we can start to do now is we can start to, so we can start to get the average. We can start to get the average. So here you can see what the IR does, hardly changes the voltage. The diffusions drops it a bit, right? The kinetics drop it even more, and then the total really causes it to die at like 32 seconds. So what we can do is we can define like when our cell is basically dead, which is maybe at like 0.4. So what we can say is we have all this plotting. So maybe we could find like what is the power density and energy density for this battery, right? So what we can do is we could say for I equals length of E total, I equals 1 to length E total, right? So we're going to go through, so if E total is less than 0.6, right? So as soon as, then what we're going to do, we'll say the index for death battery death. Death is equal to I, right? And T death, the time for death, is going to be equal, it's going to be equal to I times dt. So that's each time step. So the other thing we can do is, let's see here. So if we want to get the total energy, what we basically need is for each time step, we need to get how much energy came out, right? So we can start to, and then we're going to say end, or what's the command to jump out? It's break, I think. Break.
Yeah, it's break.
I can't remember. Is this gonna break? Is this gonna break out of this for loop, or is it gonna break out of the if statement? Hopefully, it breaks out of the for loop.
No, I think it does only the if statement.
There's a way to get it to break, do an if statement to cause it to break out of the for loop. We'll see what happens. Because we can track what I will be at the end of all this. So what you're going to want to do is we're going to take E total. We're going to multiply that by the current at every time step. So we're going to say energy is going to be equal to E total times the current times the time step dt plus energy at I minus 1. So energy, or we could say I plus 1. I guess that's okay. Energy at I plus 1. So what this is going to basically do is continue to bottom up. So we'll have energy of 1 is equal to 0. So it starts off at 0. And it's going to say the energy at the next time step is this. So this will just keep adding up. And then if this thing drops below, it should go to there. And then our power should equal to our energy divided by T depth. So this will be in watts. So this is our average power. So you take your total energy. This is our average power. Because obviously average power in watts. So our power initially is going to be very high because we're running a high current at a high voltage up here. But as it slowly dies, our power is going to go down. So let's see here. So this is going to be in energy in joules. All right, let's just give this a try. I haven't even tested this. I probably have some issues. Let's see. Okay, so far, so let's see here. Let's do some. So energy is 0. E total 6,000. Oh, we need E total of I. Okay. What I should be doing is just running this section. Especially now that it's so slow with this plotting, but Yeah, and so and then function t depth. So that basically means that it didn't run through, it didn't find this, which is weird because t total should go through, go down, and it should basically go to oh, there's only one, it's only one data point that's below 0.6. So we could always say, let's try something real of 1 plus 2i 1. So we could just take the real portion of it. Real portion of it. If the real portion, I mean, it should still, surprised it didn't jump into this, so I did. It should break. I'm gonna try it. I'm gonna see if I can learn some new stuff too. I'm gonna see if I can just run this as a section without having to make it a section. Is it gonna run this whole section up here? Yeah, see, I'd have to make this its own section. Or else we wait just to run a selected portion of the code. Run section? No. I guess you have to insert this.
Put evaluate section when you highlight it and right click it.
Okay. So it's still not finding t depth. So it's not finding this value when. So let's just make it less than one. Then it should definitely go through there. So you're saying I should go here and do right click, evaluate section?
Yeah.
Nice. So why? Oh, because I need to say of I. Always something. There we go. So, and our energy should just be constantly growing. Basically, right? So it's going to grow, 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 grow. And hopefully, let's see if it breaks out of this line. So you're right, Jose. So it's not. Let's just look that up. So MATLAB if statement to break for loop. Yeah, so it should. So the break statement should exit the loop. It's probably I'm missing another I. Let's see here. If so, because I got a t-def now, right? I got a t-def. But for some reason, it still ran. It didn't break out of this for loop as you'd expect. Wow. You skip the rest of instructions in the loop and begin. I could hire this. But
It says that yeah, it only breaks out of that inner loop. It doesn't go out of
But I just want it to break off of this one. Like I don't want it to go, I don't want I, oh, here, it says I went to 1446. But why is my energy thing 6,000 long? Maybe did we not clear everything? Oh yeah, because I just ran the section.
yeah.
It's always something. So let's clear them all. It'll run, right?
Yeah.
There we go. Good. So our finish. Yep. So our energy is not that long. So that's good. So let's do this to 0.6. Comment the energy. So our, okay. What we need to do is so total energy total is going to be energy of end. So that'll be the last one. And then this will have to be energy total. So let's see here. So our power, so pretty low. But our current's pretty low, right? So our current is 0.1, so that makes sense, right? It's about 0.1 times 1 volt. And then our energy is about total, we're getting about 3 joules. That makes sense because we're multiplying this by like 30 seconds. So yeah, so what you could do now is you could run this at like different, we could like, I mean, you could write the code to do this too, but we could also try running it at different currents. So we could try like 1 e to the negative. So let's write this one down. So I'll start like an Excel file. And we'll compare energy and power. So we'll do current, energy, power. So for this current of 0.1, for energy, we got 3.3, and for power, we got 0.09, so 0.10. All right, so let's try running it a little bit different. So let's run it a little bit slower, see what we get. A little lower current. Oh, this is nice. See, we got to run longer. We never even killed our battery. So we'll have to we need to up our time to maybe 600 seconds. The other thing we don't have in here is that our we assume our reaction area is the same as our kind of flat area, which we use like a felt electrode. So we actually we might have reduced kinetic losses. So I could change this dt a little bit too to help. So you can see our cell isn't quite even dying yet. So 60,000. Let's up this to 0.1. But you can see our energy is going up. But you'll notice now our power. Maybe I stopped it before our power ran. So you see why it's nice to have these up here? You don't need to go and change all these in here as much. So is everyone's code relatively working, or is there anyone whose code is like, it's got a bug in it and they can't quite figure out what it is?
My graphs aren't looking the same as yours.
You wanna share your screen? See if we can figure out why.
Let me see. Log into my PC.
Oh, nice. Anybody else want some help debugging your code? You can maybe rather than me like just pounding through here a bunch. Interesting. It's funny that and the only downside with this is you can't rotate it. Why at plus times 0? Interesting. Okay, so let's see what our voltage looked like this time. Did we ever kill it? Yeah, we killed it finally. Okay, good. And so now our energy total was 35. So going slower, you can see we can really pull out a lot higher. We get 35, 0.01, but our power was 0.01. So we traded off on power. So you see we got more energy when we ran slow currents, but we got less power. Let's go the other, let's try to go the, let's go one in between. So let's go like 5. This one dies a lot sooner. So just ignore this odd behavior. This type of behavior. And once it goes down here, you should just basically call it dead. So the energy total now is 6, and the power is 0.05. So here we have 6, 0.05. This was 0.05. So what you see is if we plot these, so insert scatter plot, select data. So our X values will be our energy. Oh, that's our series name. X values will be our energy. Our Y values will be our power. You see, you'll get kind of this trade-off material. So, and you'll see this. You'll typically get kind of lines like this. So, So you're going to see this with many energy devices. And that you can either choose to run it in a scenario where you have high power but you don't get much energy, or you could choose to run it in a scenario where you get high energy but low power. Right? So this is a good result. I mean, basically shows that our code's working. Okay, so the last thing I want to do is, we said this was a flow battery. So, right, so we have this model, right, that looks like this. We're actually running a model that kind of looks like this. And you have your your negative side over here reacting here, and you kind of have your positive side reacting over here, right? And you're tracking the concentration at these different nodes throughout this length. That's basically what we've been doing the whole time. This is our model. But our flow battery, you actually might have some velocity coming in. And so you might have some velocity related potentially to some incoming, so some incoming concentration. And we'll look at like this node, for example. So that's, and then if you multiply that by the area, so that's dx over the height, the thickness. So if you like, this thing had some thickness, right? You know, so this would have some thickness, this area that is going here. So you'd have some height, and so you'd have this times dx times your height, which will, we'll just call your height h. So that's the amount coming in, and then you'd have some amount coming out, right? So you'd have you'd have the concentration of that node going out times dx times h. And so, and this is, v is a velocity. So this is a velocity of the flow. So eventually we can relate this to our state of charge, right? So as you discharge your battery, your flow battery, whatever's going in is going to start looking more and more like the products overall, right? Initially, it's going to be all fresh reactants, but in the end, once you used up your entire tank, right? Because this is going to be hooked up, right, to some big tank basically, and you're going to have some tank with some pump, right? And that's going to be pumping it in here. Well, as soon as this tank all starts going from reactants to products, what's coming in your cell is going to look more like products. So we can start to have that track our state of charge. But to start, let's just see how you might do that. And I might also set it up so the velocity depends on the location, right? So we know that as something flows through, because there's no slip at the surface, the velocity profile looks like this. All right, so it flows the most in the middle and the slowest towards the edges. So let's just do a quick thing. Let's see if I can. So I'm going to come in here. And so for this line of code, basically, we need to add, it's going to have the concentration is also going to have a source term, basically. So this source term is going to be times the velocity, right? So we might say like V max. So I'll put in a V max up here. So V max, and that'll equal 0.01. And this maybe it'll be like meters per second, right? So this will be like this is a centimeter every second. We can just start slow. We'll do a millimeter every second. So V max, so the velocity will be V max, and it's parabolic, right? So it's 1 minus its x position over the length. So the x position will be x here. So 1 minus x divided by, and the total length is going to be length, 1 minus vx over the length. And this portion of this is squared. So this is just if you solved a boundary layer profile, this is what the velocity profile would look like. It would just be parabolic, high in the middle, and then at both edges. So if x equals 0, this term is this. Well, this is a little bit weird. Let's see here. So if x is 0, you're gonna get v max. We're gonna have to make this. Let's see here, because this should be its x position away from the center. So this should be, sorry, this is gonna get kind of complicated. X minus length divided by 2. Right, so if it's at the center, it should be the maximum. So that'll put this term to 0, and then so that'll put this term to 0, and we'll get the full v max. So x minus length over 2, and then it should go to 0 at the edges. So if x goes to 0, you have length over 2, so we should have a length over 2 here. This is basically the distance from the center, and this is the full distance from the center to the edge. So that's the velocity. Yeah, so I need another parentheses there. And then I'm gonna need to multiply this by, so c previous of x. So this is or sorry, you're gonna have what's coming in. So initially I'll just say this is ci. We should call this initial minus. So that way, because the hard part about doing the CI is you have to know whether it's high or low. But if we're pulling in the initial here, we can just pull in the initial. So this basically says, like, if let's say you want to have a high amount of reactant and that's starting to get low, you're gonna refresh it with the difference between that and the initial. So that's good. And this should be times, we need to times this by dx, and we need to times it by the height, which would be like the area to the half power, right? Let's say it's a square, and so the height is just half. And let's see here. So we have our v max, initial times previous times dx. Okay. All right. Well, I expect this probably to make our code explode, but it'll be interesting to see. So what I basically did, I just added a refresh, a term that adds in concentration for this one. You just have a little bit of a source term. Uh-oh, already got, oh, Vmax. So I called it Vmax, and this was in line 121. So line 121. Oh, so we're gonna need to pass it Vmax. So I'm just gonna put Vmax in here. So keep in mind, when you have these functions, if you don't pass the variable to them, it won't have any of the variables from the kind of like global area over here. And right now our battery will basically run forever, right? Because I'm constantly refreshing. But it should reach a steady state. And the next thing we can start to think about is changing this interesting. So yeah, so what you'll see. So what you see is it comes down and it reaches a steady state basically. So we don't have enough flow actually. We got to up the flow a little bit. So up the flow by a factor of 10. Because what you'll kind of see is our before it reached steady state, this V3 died. So that's why we see so these reached a steady state. So that's why we saw it die still, because we basically weren't flowing anything fast enough. So let's start writing the portion where we'll change based on the time. So we had known before, right, that the amount of species that you create, so like the moles that you create, is going to be equal times n times f times your current times the change in how much time you've been running it for, right? And so this is your like change in moles. So if we have some concentration like of overall of, let's say, of species, like let's say in your whole tank, so you have your cell, and then your cell comes out to some big tank, right? This big tank has some volume, right? So if we know we have some overall, some concentration initial, then this is going to get changed, so it's going to be plus NF I delta T, right, over the volume of the system. So we can start to have a volume of our tank and start to deplete it with this, if we can include that physics in it. If I didn't break it. Oh, it still looks like it dies slightly here. These ones aren't quite dying. So this would be 2. So it's interesting that it approaches 0 and stops. Let's see if we really flow it in there. At some point it might get a little wonky if you start flowing things too fast. I'm a little surprised that this V2 concentration is still dying at the surface. And this will do weird things to the concentration profile, right? Because you're like, so it's like if you get it too high, it might just like kind of almost turn it parabolic. We still have our V2 dying in these ones. So we have max x going to nx. Oh, I see the issue here. So this x needs to be times dx. So you have x times dx. Because that turns it into a length. X is just a number between 1 and nx. So it doesn't make that much sense. So let's put this back to something smaller. Try running it again. And so, okay, so we're gonna write this other part of the code where we're gonna have a volume, right? So maybe this will be 0. Let's say it's 1 liter. So it's 0.001 meters cubed. Okay, and then so what you're gonna have now is instead of what's coming in here as your initial, shouldn't just be your initial. So this initial is now going to be initial plus, it's going to be, I don't know if do we have N and F in here? We have F. N is 1, so we'll just leave it out. So we'll have F times current, right, times, so now we need to bring in whatever the time is, right? So that's going to be the variable t times dt, t times dt, t times dt, right? And this will be divided by volume. So now basically we're not always going at the initial. As we use up what's in our volume, we'll see less. Still not seeing the effect that we want. So let's see what this term is. Let's see what this term would be. Come on, come on. So for x, let's put in like the halfway point, nx divided by 2. Let's see here. Nx divided by 2. That one goes there, okay. And this one goes here. So we're missing we have one too many parentheses, which is okay. Here, and then let's just get rid of this part for now. Just want to see this. We don't know what nx is. Nx equals length divided by dx. Oh, we don't have a length variable in here. Come on. Oh yeah, we don't have a length variable. It's 0.001. 0.001. So our nx is 100. Let's see here. Do they not? Is it feeding in a length? It should be feeding in a length. Yeah, it's got length. Length equals 0.001. Sometimes these codes can kind of be annoying to bug. CI high, let's say. CI high times, let's say like when this goes to 0. Yeah, so you see this number is like really small. So we should kind of figure out why that is. So like this number is going to be small. You have dx times area raised to the 0.5. So basically means you have just like a little tiny cross-sectional area. But that's okay, that can be small. What's this term? And this is 1e to the negative 3. Dun, 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 dun. Let me think about it if we're missing a term here. So we have velocity times these two. So we have volume flow rate. This needs to be on a per volume basis. That's probably the reason why. Now that I think about it. So what times do we take this whole thing? Sorry that I'm winging some of this stuff. So this whole thing should probably be divided by dx times area. There we go. It needs to be on a per volume basis. It's a concentration divided by dx times area. Which one is this going to be? That one is going here. Oh, it's probably going here too. Where's this one at? There we go. Okay, so. And then, so let's see, I also want to make sure. So for example, for example, for this thing that's high, the current is positive. So that that stuff in the tank for this should actually just get lower and lower and lower. So we're actually gonna need a minus sign in here. The way it's defined. Mhm. Okay. So it definitely reaches more of a steady state. I'm gonna have to look into exactly why this drops to 0 and then it's not. Should I take a look at it? So x times dx divided by so this term is blank. That should be good there. Yeah. Initial. See previous. Scale. I'm gonna shorten our simulation up a little bit. We still have it at this really long time step, so we'll do 60 seconds. Go back up to 1 e to the -1. So I'm going to try, before we get into a little bit of this more complicated physics, just going to see the effects on the code. So we could just do something where we'll have a source term that's initial minus C. Just do something crazy simple. C previous of X. And we'll just times this by 0.001. So we'll basically just say, hey, what if there's if it's moved away from its initial, we're going to have some source term. And so this is basically what this is, but it's just the kind of a more complicated way to calculate what it should be based on the physics. Okay, so that's interesting. So extended it from 32 to like 42, but it didn't quite reach steady state. So let's keep adding to our source term, make it 10 times bigger. Uh-oh. Oh, this one didn't die yet. So here you can see it's interesting. So here you can see we got it to reach steady state concentrations, right? It went to here, reached steady state, went to here, reached steady state, right? And the voltage came and reached a steady state voltage. So this is what it should be, and it just didn't die. It just didn't die because it reached a steady state. So I'll look into exactly. There's probably just a missing parentheses or something in here with this. I'll look at that a little bit later today. But so kind of the take home message today, right, is we were able to solve for some of the overpotentials. And then we were able to take those, we were able to solve for energy and power. We noticed that in our cell there was a trade-off between energy and power. And then we can see how we can start to add a source term, although I'll still need to debug this to see if I can figure out where I'm missing a parameter. But you can see kind of the basic physics of adding a source term. Instead of these depleting, these will reach kind of these should reach a steady state. So with that, is there anyone whose code is stuck and we want to just kind of debug it a little bit? I can help you debug it. I mean, don't expect your source term like the one that I'm not even getting to run completely right yet, run right, but otherwise everyone's code's kind of working, at least solving for energy and power and giving you plots of like cell voltage.
My graphs don't look like that.
All right, let's share your screen. I'll stop sharing mine. Take a look. Okay.
So my graphs look all.
Okay, I see. So your concentrations are even a little funky, huh? Okay, let's see here. So you have dx times dt. Your dt is 0.01. Your time is 60. Your current's small. You have CH high, CH low. dx is okay. Concentrations. Because if you scroll down, even your concentrations are wonky, right?
Yeah.
And I'm guessing they probably weren't wonky before. So let me see your plots of your concentrations. Got you. So one of them, oh, so let me see your figures. Sorry, your
Oh.
lines of code for your figures. So you, yes, okay, so you got hold on, hold off. And so make sure you do hold off. So you could do all those together. It's interesting, your things are just basically not changing. Let's try this, Jose. Scroll up. Take your current, and up it, make it e to the -1. Now try running it. Do you have a source term right now?
No, I don't think so.
Let's scroll down. Scroll down into your actual solver. Right here. Okay. Okay. So go to the right. So in line 103, get rid of that. Get rid of this part. This part. Yeah, get rid of all that for now. And you can do what I do. You can just cut it and put it on like another line and comment it out just so you have it. There you go. Nice. Okay, now try running your code. There we go.
Is that something?
That's something. Okay, yeah, so all your concentrations are now right. So that's good. All right, so now scroll up. So let's look at let me see your ADAs. So for your E diffusion, let me see your E diffusion. If you scroll right on line 21, keep going right, 1,000 squared. I don't know if you need the dot, but I don't know if that'll hurt it either. Yeah, that's good. Okay. Let me see here. And that's in the denominator, right? Yeah, okay, good. Let's go, good. Yeah, perfect. Okay, then go left. Okay, so we have K not positive, that looks good. You have NF K positive. You have those. You have RT divided by, okay, you have log current divided by area divided by I not positive. You might not need the period before the multiplication sign there. Yeah, I don't think you need that one in both of those. You need that one though. It's that one. But the one below it in line 29, yeah, you don't need that one. Oh, change your I not positive there to I not negative in line 29. Yeah, there you
This
go.
one?
Yeah.
It's a negative.
Yeah, since this is all for negative.
Oh.
So yeah, so that'll be negative. And then you have concentrations of V2, which is good. And your eta kinetic is the negative plus the positive. Your Ekin is your first diffusion minus, that looks good. You have your R equals 1, so you have current. Oh, so the R should be 1 e to the -4. So R should be 1 e to the -4, because originally I put it in, that's a per centimeter squared, so you need it on a per meter squared. So that looks good. And then you have EIR. It's going to be E diffusion of 1 minus eta IR. That looks good. E total. That looks good. You have figure 1. Hold on, hold off. Kinetics IR total. All right, let's try running it. There you go. That looks good. What's the second plot right here? That's
This one.
oh yeah, you can just get rid of that one. But I mean, it's not a big deal. But yeah, I think you got it.
Let me see. And then also my energy. Okay, yeah. Before my energy was just 2 points.
Oh, let me see your energy thing. So, oh, you have energy total. That's good. Perfect. And what's your cutoff? Let me see your energy and your power. You got your power. Make sure your power, change your power to energy total divided by T def. Yeah.
Still running.
Mhm. And try hitting stop.
Oh, there's stuff.
Yeah.
I'm gonna try it again.
Yeah, sure. And just comment out your line 83 and comment out your line 7. Not sorry, suppress the output. Yeah, suppress the output of line 83 and suppress the output of line 76. Nice. Scroll up. Let's see if there's anything else on. You might do a hold off. So are you intending for all those to be plotted on the same one? So get rid of that hold
Yeah.
on and do a hold off after the last one. There you go. So if you scroll up, it might be still in the top left ones. But it looks like it's probably, I think your thing should all be right at this point.
Yeah, I think so. I think, yeah.
Anybody else's code not looking quite right? Want to take a look, see if we can figure out what it is. All right, so feel free just to email me, and if when we're talking face to face, I can also just try and help debug some of the codes. So we're not going to meet. Let's not meet this Thursday. I had something come up all day Thursday. But maybe for next week, what would be good is if folks, they're interested to continuing to do a more specific model, I think it's time maybe to transition now to your current system, right? And so for next week, maybe we could have each person could kind of make a little schematic of the geometry of their system, and then they could talk about, all right, this is the strategy I would have for modeling it based on what you know now. And you could even have a list of, all right, these are the things I don't understand how I would model yet. And so, for example, maybe there's a porous diffusion layer in your system, right? And you wouldn't understand, all right, how do I take into account the effects of this porous diffusion layer? But you might start with, all right, this is my actual system. These are the things I don't understand how to model. And then you might say, okay, well, is there a way I can simplify the system as kind of a start? And like, is there a simplified system that I can model first? And then I can continue to build up into kind of the full system as realistic as possible. So if, and to do this, I would also suggest looking at some papers, trying to find some papers of people who have done modeling of your system or a very similar system. And we can go around and maybe just take, 15, 20 minutes a piece, and we could look at it, and me and other folks could begin to say, okay, this would be a good plan for you to get started. And we can help each other in that way. And we might see there's certain groups of people that might be doing the exact same type of modeling, and certain, we might all fall into 2 or 3 categories, right? And then you kind of know, all right, let's split into these 2 or 3 categories, and we can work together a little bit, since we know our models are going to try and be simulating almost the same physics, right? So well, let's take a week since I know that's going to be kind of long. I have availability Friday if people need to meet to like kind of check in to see how they're doing. But yeah, so let's see if you can do that. You know, what does your system actually look like? You know, how would you model it if you could? What don't you know? And is there a simpler system, right, that you could think of to start with? And then if you have any papers to help support that, that would also be great. And I'll figure out how to do the more refined version where we could actually put in the velocity and see if we can get it reaching a better steady state. So I'll figure out what's going on with that, and I'll have that ready for next week. But yeah, I mean, I think at this point the other thing, I guess, the one thing we haven't been doing is tracking any of the like non-active species. So sometimes you might need to track some of the negative charge carriers. And then you can also include effects like migration, right? The effect of the electric field on moving things around. So maybe in 2 weeks or something, I'll plan to pair something about how would you model, if you wanted to do a more detailed model that included migration and not just diffusion, which is useful in cases where you don't have a big buffer solution. So if you dissolve in a salt in your solution, like a bunch of NaCl or KCl or sulfuric acid, you probably don't, the migration's not as big of a deal. But if you have a system where that's not the case, then it can be critical to track the other charge carriers in your system. But I don't think there's actually that many people here who have a system like that. That was actually just Maya's case, and so that's why we had to kind of go a little extra complex on hers. But yeah, and I think this will also help you understand, like, all right, what are the losses in your system, right? And these three components, right? You have these kind of concentrations at the surface, and you also have your kinetic losses. You also have your IR losses. So I think that'll help you, even if you're just experimentalist, be able to kind of try and understand, you know, what are the things causing your system not to perform at the highest level it can perform. But yeah, with that, I think we're already 15 minutes over, so I'm going to shut off the recording.